All right, for this one, we're going to do some calculations that are going to get specific with getting how much heat is transferred. And our formula for that all the way across is going to be Q equals mc times delta T. Q is the amount of heat, m is the mass, C is the specific heat, and delta T is the change in temperature. And just as a reminder, delta T would be T final minus T initial. It's always going to be the change in temperature. That has to be in Celsius. That's why these C measurements are in Celsius. So as we go through these problems, we want to do the guess method with it, where we identify the things that we know and the thing that we don't know. So 2,500 joules of heat, that's our Q, is added to a 0.5 kilogram metal sample. That's the mass. The metal has a specific heat of 250 joules per kilogram. That's our temperature. And it wants to know how much the temperature will change. So our knowns, our Q is 2,500 joules. Our mass is 0.5 kilograms. I lied over here. That's not T. That's our specific heat of C. C is 250 joules kilograms per degree Celsius. And our unknown is delta T. So we're going to use Q equals mc delta T, and we're going to plug in what we know. We know Q, 2,500, equals m, 0.5, times C, 250, times delta T. So we are going to divide by 0.5 times 250. And we're going to do that on both sides. 0.5 times 250 is 125. And when we do that, our delta T comes out to be 20 degrees Celsius. So that sample is going to change by 20 degrees Celsius. So we're going to do the same thing all the way through. 75,000 joules of heat, that's Q, is added to a 2 kilogram metal sample, that's M. The metal has a specific heat of 250, that's C. And if the initial temperature of the metal is 15, so that's T initial, what will its final temperature be? T final. We don't know that. So here's what we're going to do. We're going to find delta T first. Our Q is equal to 75,000 joules. Our mass is equal to 2 kilograms. Our C is equal to 250 joule kilograms per degree Celsius. And we want delta T. That we don't know. So 75,000 is equal to 2 times 250 times delta T. So we'll divide by 500 because that's 2 times 250. And that's going to give us 150 degrees Celsius. That's my change in temperature. And that's an increase. If that's the case, T final is T initial plus delta T. All right, so my final temperature is going to be 15 plus 150, and my final temperature comes out to be 165 degrees Celsius. Next one, a student heats up a sample that is 2.5 kilograms. That's our mass, from an initial temperature of 12 Ti to a final temperature of 30 Tf. During this time, it absorbs this much heat, Q. Calculate the specific heat, that's C. That's the thing that we don't know. So we know that the Q is 54,000 joules. We know that the mass is 2.5 kilograms. We know the T final and T initial, so we can get delta T. We'll just kind of do that over here. Delta T is T final minus T initial. So 30 minus 12, delta T is 18 degrees Celsius. And then we are looking for capital C. So we'll put all that in. So Q is equal to mc delta T. So 54,000 joules is equal to 2.5 times C, which we don't know, times delta T of 18. So we'll divide by 2.5 on both sides, and we'll divide by 18 on both sides. And that's going to give us C. Now, you guys are prone to make mistakes when you do this in your calculator, so I want to show you what you're doing. For this one, we're taking 54,000, and we divided it by 2.5, and we're dividing it by 18. That's how you need to put it in your calculator. That's going to give you your C. Or you could look at it as 54,000 divided by those two things together, 2.5 times 18. Still get 1,200. There's just a couple different ways to put it in your calculator. So C comes out to be 1,200, and our units on that are joules times kilograms per degree Celsius. And that's not right. An engine made of 12.8 kilogram aluminum, that's our mass, is heated from 15, T initial, to 100 degrees Celsius, T final. How much heat did it absorb? That's our Q. And as we adjusted this, C for aluminum is equal to 900 joules per kilogram degree Celsius. So Q is equal to MC delta T. We have our mass, 12.8 kilograms. We have our C, 900 joules per kilogram degree Celsius. And we have our delta T, where we go from 15 to 100. That's a gain in temperature of 85 degrees Celsius. So we multiply all those together, and we get our Q to be 979,200 joules of energy. Student wishes to melt some copper to create a new statue of her physics teacher, which is very nice. She has a butane tank that's capable of releasing a whole bunch of joules of heat. What's the maximum mass of copper she can heat from 8 degrees to 1,085? So for this is how much heat we have. That's our Q. We are looking for the mass, so mass is unknown. For our delta T from 8 to 1085, that makes delta T 1070. I'm sorry. That makes delta T equal to 1078 degrees Celsius. And what we are looking for is the maximum mass of copper. And just like before, you need the C. C for copper, like I gave you, is 386 joules per kilogram degree Celsius. So Q is equal to 850,000 joules. Mass is unknown. Delta T is 1,078 degrees Celsius, and C is 386 joules per kilogram degree Celsius. So we're going to use our same formula. Q is equal to MC delta T. Put in our Q. 850,000 is equal to M times 386 times 1,078, because it's our delta T. We're going to divide both sides by 1,078. We're going to divide both sides by 386, which means over here we divide by 1078, and we divide by 386. Put that all into our calculator again, and we'll see that to be 2.04 kilograms of copper. It's going to be a lovely statue. 6. A hot tub holds 480 kilograms of water. That is our mass. On a cold day, the initial temperature is 4 degrees Celsius. and it needs to reach a temperature of 5 degrees Celsius. So what we want is a delta T of 46 degrees Celsius. So for this, we also need, as we have been given, the specific heat for water. The specific heat for water is 4,182 joules per kilogram degree Celsius. So we're going to use that in order to find it. So A wants to know how much heat we need. A is the heat that we need. So Q equals mc delta T. We're looking for Q. We know mass is 480 kilograms. We know C is 4,182 joules per kilogram degree Celsius, and we know delta T is 46 degrees Celsius. So we're just going to plug all that in and get our total heat. This is a large number. We get 92,338,560 joules of heat. That's a lot of heat. In context, we have propane that releases this many joules of heat per kilogram. So we want to know how many kilograms we've got. So it's a conversion, kind of a throwback to chemistry. But if we have 92,338,560 joules of heat, we want to convert that from joules to kilograms. Right, so we have joules on top, we need joules on the bottom, and our conversion factor needs kilograms on the top. And for our little conversion factor here, joules of heat per kilogram, that's what we're going to use. We have 4.65 times 10 to the... Oh, no, that's backwards. That's my joules. I apologize. We have 4.65 times 10 to the 7th joules per 1 kilogram. So we're going to take 92,338,560 joules and divide it by that to see how many kilograms we get. Joules on top, joules on bottom, that goes away. And we end up with 1.99 kilograms of propane. If propane is 81 cents per kilogram, how much will it cost to heat the hot tub? And again, we're going to do another conversion, so 1.99 kilograms, and we want to convert that into dollars. So we need kilograms on the bottom, dollars on top. We have 81 cents per kilogram, so 1.99 times 0.81 gives me $1.61 to heat the hot tub. And if you're wondering, I am much more concerned that you know how to do this, find the amount of heat, than either of the other parts. A race car engineer is studying the heat-absorbing properties of a new ceramic alloy he intends to use. He heats the sample. So this is all stuff for the alloy. That's its mass, to a temperature of 500 degrees Celsius. That's its initial temperature, and places it in a thermally sealed container holding 2 kilograms of water. That's a different mass. We'll make that blue. That's water's mass at an initial temperature of 20 degrees Celsius. That's initial temperature for the water. At the end, the final temperature for both is 30 degrees Celsius. A asks how much heat was gained by the water. So for the water, I know that the mass of the water was 2 kilograms. I know the specific heat of water is 4,182 joules per kilogram degree Celsius. And my delta T for water, well, the water started at 20 and it ended at 30. So the delta T for water is 10 degrees Celsius. That's positive because we're gaining that. And we want to know the Q. That's our first step. Find out how much energy we're talking about. So Q is equal to mc delta T. We know all of those things, so 2 kilograms times 4,182 joules per kilogram degree Celsius times 10 degrees Celsius. That makes the heat absorbed by the water, gained by the water, 83,640 joules. That, to put some words on it, is the heat gained by the water. How much heat was lost by the ceramic? Well, the heat that the water gained had to come from somewhere. And it comes from the hot ceramic. So, the amount of heat gained by the water is equal to the amount of heat lost by the ceramic. And since that heat is lost, so now that we have the heat lost by the ceramic, we can find the specific heat of the ceramic. So we know that the heat lost is negative 83,640 joules. And again, that negative sign, lost energy. So we have the heat lost by the ceramic. We have the mass of the ceramic. It was half a kilogram, so 0.5 kilograms. We have the change in temperature of the ceramic. It went from 500 degrees down to 30 degrees. That is a loss of 470 degrees Celsius. And what we want to do is find the specific heat of this new special ceramic material. So, Q equals mc delta T. We have everything except for C, so negative 83,640 joules is equal to the mass. 40,000 is equal to the mass, 0.5 times C times delta T, which is negative 470. We're going to take and divide both sides by 0.5. We're going to divide both sides by negative 470. 0.5 goes away, negative 470 goes away. And that gives me C as, and you know what, we'll do this with the fancy calculator, just again to kind of reiterate how you will be using the calculator for this. So clear that out of there. Negative 83,640 divided by 0.5, and we divided both sides twice, so divided by negative 470. We're dividing by both of those things. Gives me a specific heat of 335.9. And that's joules per kilogram degree Celsius.